All right, chapter 7 involves chemical bonding, a very important topic in chemistry. So there's actually three types of chemical bonds, two types of bonds that occur between atoms or ions to make compounds. They are ionic and covalent bonds. So we'll first talk about ionic bonds. Ionic bonds occur because of the electrostatic interaction of ions. So that term electrostatic refers to attraction between oppositely charged particles. So we have ions that are attracted to each other, and this produces something called an ionic bond. Ions form when electrons are transferred between atoms or groups of atoms. So we have a transfer of electrons from one atom to another atom, producing oppositely charged particles called ions, which again, these stick together. Ionic bonds often occur between metals or atoms that have low electronegativities and nonmetals or atoms that have high electronegativities. So it's not so much that it's a bond between a metal and a nonmetal. Better description would be a bond between an atom with a low electronegativity and an atom with a high electronegativity. In most cases, this refers to metals and nonmetals, respectively. Covalent bonds, very different, occur when atoms share one or more pairs of electrons. This often occurs between atoms that have high electronegativities. So both of the atoms have relatively high electronegativities. This could be two or more nonmetals, or it could involve metalloids as well. So typically it's two nonmetals bonded together. They will share one, two, or three pairs of electrons. Covalent bonds can occur between different nonmetal atoms, or it could be the same ones, as is the case in the diatomic molecules, where you have two of the same atoms that are bonded to each other. Next up, very important, knowing the properties of ionic and covalent or molecular compounds. We'll start off with physical states. So ionic substances are solids at room temperature, and they typically have rather high melting points above 400 degrees Celsius. You don't have to know that value. Just know that the melting point of an ionic compound is pretty high. Think about salt, for example, sodium chloride. You can't melt salts on your stove. It doesn't get hot enough, so you need really high temperatures to melt ionic substances. Covalent substances, covalent compounds, or molecular compounds can exist as solids, liquids, or gases at room temperature. And then they have typically low melting points, below 300 degrees Celsius. Some of them even much lower than that, especially if we have something that's a gas at room temperature, let's say. Of course, its melting point then is going to be far below room temperature. So though they could exist as solids at room temperature, the melting point of any molecular solid is going to be much lower than an ionic solid. Next up is solubility. We'll start with solubility in polar solvents, such as water. Ionic substances, most are soluble in water. Solubility rules will help us to predict if an ionic substance is soluble or not. Molecular compounds or covalent compounds, many are not soluble. Many are, but many are not. Remember to predict if a molecular substance is soluble or not. We use like dissolves like. So the only molecular compound that's going to be soluble in water would be anything that is like water, polar. So many covalent compounds are nonpolar, therefore are not soluble in water. Solubility in nonpolar solvents such as benzene or carbon tetrachloride is another common nonpolar solvent. Ionic substances dissolve in polar solvents but not in nonpolar solvents, so they're not very soluble. Conversely, covalent compounds or molecular compounds, many are soluble. Again, like dissolves like, so any nonpolar substance will dissolve in a nonpolar solvent such as benzene. Next up, we have electrical conductivity. We'll start with the substance when melted. There's a name for that. When you have a solid that exists as a liquid, it's called molten. So molten compounds. Molten ionic compounds are good conductors of electricity. Again, in order for something to conduct electricity, you need mobile charged particles that are able to move around. The particles in a liquid can slide past one another, so those ions, the mobile ions in a molten ionic compound, allow for electricity to be conducted. Molecular compounds, when melted, are poor conductors of electricity and not made of ions, so not going to conduct electricity. Conductivity in solution. So ionic substances are good conductors of electricity. We've talked about this before. Of course, we're talking primarily about the soluble ionic compounds. Because they produce lots of ions, will be excellent conductors of electricity. Covalent or molecular compounds, not made of ions. Put them in water, they don't dissociate. They dissolve, but they don't dissociate, and therefore will be poor conductors. All right, switching up to Lewis or electron dots formulas of atoms. A little review of valence electrons. Remember, these are the electrons in the outermost principal level or highest principal level of an atom. These electrons are the important ones. These are the only important electrons in an atom. These are the ones that are responsible for the physical and chemical properties of an element, along with what type of bond an atom may form. Only S and P electrons are valence electrons in atoms, so though some metals can lose D electrons, we don't typically talk about the D electrons as being valence electrons, so it's only the ones in the S and P sublevels. Consequently, only representative elements have valid Lewis structures. Go ahead and pause the video and take a look on page 752. Rather, that's table 7.1 on page 252. So we have some examples of Lewis structures for atoms. Remember, the dots represent the valence electrons, and so we just put the same number of dots as there are valence electrons around the symbol up to 8 dots, especially for the noble gases as we see. In group 8A it says in your book, or if we have an element in group 1 which has 1 valence electron, we'll put 1 dots around the symbol. Those dots don't really matter. It doesn't really matter where they go as long as you have the correct number of dots. So it doesn't have to look exactly like what's shown in the book. So again, this Lewis structure reflects the structure of the S and P sublevels in an atom. We will talk more about Lewis structures when we describe how the different types of chemical bonds form between atoms. All right, some more with ionic bonding. First of all, an atom or group of atoms that carries an electrical charge is called an ion. There's 2 types. You have cations and anions. Cations are positively charged ions. They form when an atom loses electrons or when an atom is oxidized. Anions are negative ions, and they have a negative charge because that atom has gained electrons or has been reduced. If you go to page 255, you can see an example of what's called a crystal lattice. A crystal lattice just consists of a whole bunch of cations and a whole bunch of anions all stuck together. So here we see a crystal of sodium chloride. I believe I've shown you this model in my class before, where we have the negative and positive ions that are attracted to each other to form some solid substance. So let's do this. Let's show how an ionic bond forms between sodium and chlorine using these different methods. So here's what we're going to do. Let's say you took some sodium metal and you place it in a container of chlorine gas. What's going to happen? Well, a chemical reaction occurs, and that chemical reaction produces sodium chloride. So how do you end up with some sodium ions and chloride ions all stuck together? So let's draw first using orbital diagrams. So go ahead and pause the video, draw the orbital diagram for sodium, and right below that, draw the orbital diagram for chlorine, and then I'll show you what happens when the ionic bond forms between these two. So let's start with sodium. Sodium has 1 valence electron. What does sodium need to do to become stable? It needs to lose its 1 valence electron. Take a look at chlorine. Chlorine has 7 valence electrons. What does it need to do to become stable? It needs to gain 1 electron. So these two are a perfect match for each other. Sodium wants to lose an electron. Chlorine wants to gain an electron. So in fact, that electron that I showed in a different color, yellow, is going to be transferred from the sodium to the chlorine. So what happens as a result of this transfer of electrons? Well, sodium loses an electron, and because of that, it develops a positive charge. Chlorine gains an electron, and because of that, it develops a negative charge. And what do positively charged and negatively charged particles do to each other? Well, they attract, so these two ions are going to stick together and form what is called an ionic bond. All right, let's kind of show the same thing, this time using ionization equations. So let's start off with the ionization equation for sodium. So sodium loses an electron to form Na+, a sodium ion. What happens with that electron? Does it just float off into space? No, that electron goes somewhere. In fact, that electron goes to chlorine. So trying to show kind of together here. So the electron that sodium loses is transferred to chlorine. So chlorine, individual chlorine atoms gain an electron to become chloride ions. Again, we see two ions form. Simultaneous formation of two oppositely charged particles. And those oppositely charged particles will stick together. Ionic bond. Let's show now with Lewis structures. So go ahead, pause the video, draw the Lewis structure for sodium next to that of chlorine. So just put them close to each other. So we have sodium with its 1 valence electron, chlorine with its 7 valence electrons. Chlorine is much more electronegative than sodium. So when you put these substances together, what happens is the chlorine physically rips the electron off of sodium. In fact, I'm going to show that electron in a different color just for emphasis. So just like before, we got the sodium cation that forms, a chloride anion that forms, and those two ions stick together, making sodium chloride. All right, very, very important factors affecting the strength of an ionic bond. We're going to use Coulomb's law. So if you got some room to the right or above letter D, let's write the equation for Coulomb's law. So it could be lowercase or capital Q's. I've seen it both ways. So F equals KQQ over R squared. K is just a proportionality constant. So F here is force of attraction. It could be force of repulsion. Q1 and Q2, those are the charges of the ions. Since they're oppositely charged, F is an attractive force. If Q1 and Q2 are the same charge, F would be the repulsive force. So it works for attractive and repulsive forces. So Coulomb's law applies in any situation where you have attractions between oppositely charged particles, such as the nucleus of an atom and its electrons. Here we're talking about the attraction between cations and anions. So if we look at the equation, F, how do we increase the value of F? Well, if either Q1 or Q2 increases, then F will increase. So what we see here is that the strength of an ionic bond is directly proportional to the product of the charge magnitude. So now I don't want to take into consideration that one of the charges is negative. So just the magnitude of charges. The greater the magnitude of the charges of your ions, the stronger the ionic bond, and the higher what is called lattice energy. Lattice energy refers to the energy required to break ionic bonds in an ionic compound. Notice we have R squared there as well. R is the distance between the ions. So as R increases, F decreases. So the strength of an ionic bond is inversely proportional to the square of the distance between the bonded cation and anion. So we have to look at ionic radii. The bigger the ions, the weaker the force of attraction, or the weaker the ionic bond, and the lower the lattice energy. I guess I messed up. I should have put the equation underneath there, but there's the equation for you. Let's take a look at some examples. So let's compare the lattice energies, or the strength of the ionic bonds, and this relates also to melting point. So the stronger the ionic bonds, the higher the melting point. So sometimes it's asked in terms of melting point, sometimes just asked in terms of strength of the ionic bond. So let's take a look at a couple things to compare. So let's compare lithium fluoride to beryllium fluoride. Actually, I'm going to do a different example because this one's a little bit tricky. All right, let's compare sodium chloride to magnesium chloride. Which one of these compounds has the strongest ionic bonds? Or which one of these compounds has the highest energy? Or which one of these compounds has the highest melting point? So all of those three things are related. So the first thing we always want to look at are the charge magnitudes, the magnitude of charge of the cation and anion in each compound. So in sodium chloride, the cation has a charge magnitude of 1. The anion also has a charge magnitude of 1. So if we multiply those together, we get the product of the charge magnitudes being just 1. Let's take a look at magnesium chloride. Now notice something, I'm not taking into consideration that there are 2 chloride ions. I just want to look at the charges of the ions in the compound. So magnesium has a charge of +2, chloride has a charge of -1. Again, let's look at the product of the magnitude of these charges. Since the product of the magnitude of the charges in magnesium chloride is greater than that of sodium chloride, then we would say that magnesium chloride has stronger ionic bonds, higher lattice energy, higher melting point. Now, something else that we have to keep in mind are the sizes of the ions. So in this case, the ions in both compounds are the same size. Well, chloride is the same ion, so it's definitely the same size. Sodium ions and magnesium ions, though, they have a very similar, very different, sorry, I can't talk. Sodium ions and magnesium ions do have a different ionic radius, but they are pretty close. And so for this example, we're going to say they're about the same size. And so ultimately, what determines the strength of the ionic bond is the charge magnitudes. Now let's take a look at another example. Again, in what situation is the ionic bonding stronger, or the higher lattice energy, higher melting point? So let's first look at charge magnitudes. So notice that in both compounds we have a product of charge magnitudes of being just 1. The charges of the cation and anion in both compounds are the same. So next thing we want to look at is the size of these ions. And we can use atomic radius, even though these are ions. Atomic radius would be good enough. So let's compare the cations. Sodium is bigger than lithium. Let's look at the anions. Chloride is bigger than fluorine. So in sodium chloride, both the cation and anion are larger than in lithium fluoride. So going back to Coulomb's law, as R goes up, this distance between the ions, so the bigger the ions, the greater the distance between them, the weaker the attractive forces. So the ionic bonding in lithium fluoride is going to be stronger than in sodium chloride because both the lithium ion and fluoride ion are smaller than sodium ion and chloride ion. Let's try another one. All right, go ahead and try this one out. Which one has has stronger ionic bonds or a higher lattice energy or a higher melting point? Go ahead and pause the video and see if you can answer that question. So the ions in these two compounds are about the same size. They're relatively close in size. Difference here again is charge magnitude. So the charge magnitudes, the product of the charge magnitudes in aluminum oxide is greater than that of magnesium fluoride, giving aluminum oxide a higher lattice energy, higher melting point, stronger ionic bonds. All right, let's talk about covalent bonds. We have two opposing factors that need to be addressed when talking about a covalent bond forming. One of them is that electrons in one atom are attracted to the nucleus of the other atom that it is bonded with. And the nuclei of the bonded atoms, so the nucleus of each of the bonded atoms, and the electrons of each of the bonded atoms repel each other. So the nuclei repel each other, the electrons in the two atoms repel each other. So we have two opposing forces, force of attraction between nucleus and electrons of another atom, and force of repulsion between the nuclei of the two atoms and the electrons of the two atoms. If you take a look in the margin on page 259, we see both of these. So the red represents the force of repulsion between the nuclei and the electrons. And then we see the blue represents the attraction between the nucleus of one atom and the electrons of another. So what happens? How do we get these things to stick together? Well, it must mean that number one is greater than number two. Force of attraction greater than force of repulsion. Let's do this. There's a graph on the bottom of page 259. So we're going to draw the same thing as that. So let me label the axes here. So let's start off with a very short internuclear distance. So internuclear distance is the distance between the two nuclei of the bonded atoms. If they're really close together, the energy is going to be high. But as we pull those atoms apart from each other, that repulsive force is going to decrease and the attractive force is going to increase. And so at some point, some distance, some optimal distance between the nuclei, we reach the optimum energy. So least amount of energy where we have a balance between the attractive forces and the repulsive forces. If we start to move those nuclei further and further apart, again, the attractive forces are going to weaken and the energy will increase. So where that energy is a minimum represents the optimum distance between the nuclei in that covalent bond. And so that's how far apart the atoms will be from each other, where the attractive forces and repulsive forces counteract each other. And we get the most stable arrangement of those atoms. All right, let's go through the properties of covalent bonds. First one's pretty easy. Bond order simply refers to the number of bonds between bonded atoms. For example, a single covalent bond has a bond order of 1. A single covalent bond involves a sharing of 1 pair of electrons. A double covalent bond has a bond order of 2, and it involves a sharing of 2 pairs of electrons. And you know what's next? A triple bond has a bond order of 3, and it involves the sharing of 3 pairs of electrons. There is no such thing as a quadruple bond. So a triple bond, or 3 shared pairs of electrons, is the most pairs of electrons that 2 atoms can share. So we just talked a little bit about it. Bond length is the internuclear distance between the bonded atoms, or simply the length of the covalent bond. This varies inversely with bond order, meaning the higher the bond order, the shorter the bond. There's a table in your book on page 261. It shows a relationship between bond energy and bond length, and bond order and bond length. So double bonds are shorter than single bonds, and triple bonds are shorter than double bonds. And we'll get to bond energy next. Bond energy as opposed to lattice energy. So lattice energy refers to the strength of an ionic bond, when you see this term bond energy, this refers to covalent bonds. So technically, by definition, it is the amount of energy in kilojoules per mole released when a bond forms. So it's important for you to know that the formation of covalent bonds, or any chemical bond for that matter, is exothermic. It releases energy. Remember, why do atoms form chemical bonds in the first place? It's in order to become more stable. So less energy, more stable, less energy. So what happens to that excess energy? That energy is released to the surroundings. Now the opposite's also true. When you break a bond, or anytime you separate things that are attracted to each other, this requires energy. So bond energy is the energy absorbed or required when covalent bonds are broken. So bond energy varies directly with bond order. So what does that mean? Double bonds are harder to break than single bonds, and triple bonds are harder to break than double bonds. And you can see that data on page 261. Double bonds, if you look at a carbon-carbon double bond, it has a higher bond energy than a carbon-carbon single bond. And also a carbon-carbon triple bond has a higher bond energy than a carbon-carbon double bond. Bond energy varies inversely with bond length. So again, the shorter the bond, the harder it is to break. Or the shorter the bond, the more energy is required to break that bond. The opposite is also true. So please review why chemical bonds form between atoms and whether the bond between two atoms will be covalent or ionic. That depends on differences in electronegativities. And make sure you know the properties of covalent bonds. All right, thanks for watching.